Next up, it is my pleasure to introduce, I think that Richard Obousy was the first president of Icarus Interstellar. That is true. Dr. Richard Obousy. I'm not done introducing, I'm sorry. In addition to that, he's one of the top theoretical physicists in the entire world. To be in the same room with Richard Obousy and Dr. Cuvier is a thrill for me. I hope it is for you. Richard?
Great. Well, all right, well, good afternoon, everyone. Pleasure to be here today. My first visit to Monterey, beautiful city. It's good to see some familiar friends, familiar faces, and I look forward to getting to know people who I've not met over the next few days. It's a real pleasure to hear Miguel speak earlier. I was 17 years old when his paper came out in 1994. I first actually came across the paper in 1999 when I was working on my master's degree at Leicester University in England, Master of Physics with Space Technology, and really inspired me to know that there were real physicists, real theoretical physicists working on the problems associated with interstellar flight, more specifically with the possibility of superluminal travel. I'd been interested in interstellar travel for a long time, grew up on a diet of science fiction books and Star Trek, and I remember discovering Arthur C. Clarke's 2001: A Space Odyssey in my early teens, and really that set me off on a personal journey, a personal quest. So, structure of my talk, I'm going to be given an overview of what interstellar travel is, and then talking about why it's so challenging, talk about the physics behind it. And then we'll talk about possible near and midterm solutions to the interstellar problem. And then I'm going to introduce an idea I had when I was at graduate school that I developed over a few years between 2005 and 2008. And it looks at the problem of superluminal flight from the perspective of quantum field theory, which is a departure from what's traditionally used. General relativity is typically the tool that is used. So interstellar flight involves sending probes, either robotic or perhaps one day crewed, to other star systems, to other solar systems. So we've visited with probes every planet in the solar system. We've sent human beings to the moon, but clearly we've never been to other star systems. And I think there are a number of reasons that we may want to engage in interstellar flight. Firstly, there are scientific reasons. The space between the stars is not empty. It consists of particles and fields that are of interest to physicists, to astrophysicists. Of course, there's studies of the target star when we get there. Studies that we have to do in situ that we can't do here from Earth or Earth orbit. And then, of course, there's the tantalizing results coming out. We now know that there are several thousand confirmed exoplanets. And so if we could do in situ studies of those planets, take a picture up close, check out the atmospheric composition, a host of other things that we could do there that we can't do from here, I think that's a very compelling reason for us to engage in interstellar travel. And then there's even more tantalizing possibility of astrobiological studies. So we know that there are Earth-sized planets out there, that there are rocky planets out there. We know there are planets that are in the habitable zone. So this is the habitable zone being the region where liquid water can exist. So I think there are a number of highly compelling reasons to go. Other motivations, the longevity of human civilization. We know there have been a number of mass extinctions that have occurred on the planet, the last being the Cretaceous-Paleogene extinction about 66 million years ago. Nature doesn't distinguish between civilization and non-civilization. There's nothing to prevent a future mass extinction from occurring. Of course, we could mitigate that risk by populating other planets in the solar system, but I think we further de-risk the possibility of there being no more human civilization if we perpetuate who we are one day to the stars. And then my personal favorite, I think human beings, I think we're a curious species. I think we're energetic, and so interstellar travel could be just a means to an end. Just the purpose of doing it is for the sake of doing it, an expression of a curious and energetic species. But it's going to be challenging, it's going to be hard, and it's going to be expensive. So we have several probes right now, 4 probes that are currently in what we call interstellar space. To give you some sense of scale of the problem, Voyager 1, which was launched in 1977, been traveling for 40 years. Voyager 1 is traveling at 11 miles per second. It's not traveling to Proxima Centauri, which is the closest star. If it were traveling to the closest star, it would take about 80,000 years to get there. And to give some context, to give some sense of scale of the problem, if we shrink the distance from Earth to Proxima Centauri to be equivalent to circumnavigating the Earth once. So this is just a thought experiment. Instead of going from Earth to Alpha Centauri, we're going to shrink that scale and say, okay, let's say Voyager 1 has to circumnavigate the Earth one complete revolution. Transpires, Voyager 1 has only traveled about 3 miles. And so from where we are today, we'd almost be at a little golf club just down the road. So that really gives some sense of scale of just how far we have to go. And the challenge becomes more apparent if we consider one of the most elementary equations of rocket science, the Tsiolkovsky rocket equation. Over there on the left is the mass ratio. That's the ratio of the mass of a fully laden rocket with fuel to a rocket that's empty and fuelless. And over on the right, delta V is how much you want to change your velocity by. Essentially your change in speed. ISP is the specific impulse, which is a measure of the effectiveness, if you like, of the propulsion fuel that you're using. And then G is a constant, 9.81. And if you wanted to get to one of the closest stars, Proxima Centauri, for example, on timescales of a human lifetime, around 40, 50, or a working scientist's lifetime, around 40 or 50 years. And if you plug the equations using chemical propulsion to reach 10% the speed of light, which would get you to a nearby star around about a human lifetime, you would need more mass than there exists mass in the known universe. You would need more chemical propellant than there is mass in the known universe. So it's impossible. The problem can be mitigated. That's for a single-stage rocket. The problem can certainly be mitigated by multi-staging, but it gives you some sense of the scale of the problem. I mean, it's still going to be a huge problem, even with tens or hundreds of stages. So chemical rockets are vastly inadequate for interstellar propulsion. But one way to think about this, I believe, we tend to vastly underestimate what we can accomplish on long timescales. We overestimate what we can do on short timescales. I think many of us in this room have probably started a project thinking it would take 1 or 2 months, and it ends up taking 6 or 7 months. We definitely overestimate what we can accomplish on short timescales. But on long timescales, what we can accomplish is borderline unfathomable. Here's a particularly salient example, the Kitty Hawk, that flew in 1903. And I want you to take a look at that flimsy-looking contraption, mostly made of wood, with a man traveling head first. So it was the first heavier than air, first controlled, powered, and sustained human flight. Yet it was just a little over 50 years after that flimsy contraption that we had transatlantic jets ferrying passengers across continents. So just about 50 years later. I remember watching Star Trek in the 90s. They had this wonderful device called the pad, which could solve equations and could talk to you and seemed to be able to do just about anything. And I truly believed that was 24th century technology. I thought it would be hundreds of years until human civilization was utilizing technology like that. Yet 15, 20 years later, we take for granted, we don't even give a second thought to the fact that all of us have something more powerful than a pad. Here's another example, the experimental verification of the atomic substructure of matter. So we know that matter consists, in the atomic model, of an electron cloud orbiting a nucleus consisting of neutrons and protons. Of course, there's further structure behind that, quarks, perhaps superstrings. But in terms of that elementary model of protons, electrons, and neutrons, we didn't experimentally verify the electron until 1897. The proton, 1917, and then 1932, Chadwick put the final piece to the puzzle and experimentally verified the neutron. So from 1932, it took a little over 30 years, or about 30 years, till the testing of the first nuclear rocket. So Project Kiwi was a facet of NERVA, Nuclear Energy for Rocket Vehicle Applications. It was a nuclear rocket program conducted by the United States in the 1950s. And so, again, from the completion of our understanding of the nature of matter, it was a very short leap, time-wise, to get to turning that understanding to technology, specifically for propulsion. And then moving on to the next slide. Okay. Having some difficulty. Is there someone who can manually move the thingy forwards? Okay, there we go. Let's see if this is working again. Okay, good. So just to reiterate, we tend to underestimate what we can accomplish on long time scales. So I think this really sort of brings home the point. We have the flight of the Kitty Hawk in 1903, Sputnik in 1957, 4th of October, and then of course we've got Neil Armstrong landing on the moon in 1969, and then around 1990s, 2000, we had the completion of the International Space Station. And so just want you to conceptually grasp just how far we've come in approximately 1 century. And so I don't think, if you look at from this to this, I don't think it's a huge leap to think that within another century we could be building starships in orbit around one of the moons of the gas giants. Earlier I talked about how chemical rocket propulsion was vastly inadequate for interstellar propulsion. But fortunately, liberating energy from matter is not limited to simply chemical reactions. We know of a number of other ways of liberating energy from matter. Nuclear fission, thermonuclear fusion, and antimatter. So fission, bombarding high atomic number elements with rapidly moving high kinetic energy neutrons, splitting them apart, creating fission fragments, giving off kinetic energy in the process. Fusion, so the fusing together of fast-moving low atomic element matter, creating matter of higher atomic number, and again giving off kinetic energy in the byproducts and radiation. And of course, we've known of the existence of antimatter for some time. It's predicted, I think, Paul Dirac initially came up with the idea of antimatter, suggested that for every particle there was an equivalent antiparticle. And of course, when particles and antiparticles meet, they annihilate each other almost perfectly, according to Einstein's equation, E equals mc squared. And over here on the middle, this column gives you a representation of how much energy per unit kilogram of mass each of these physical processes liberates. So you have this much energy, 1.5 times 10 to the 7, joules per kilogram for chemical energy. You get 1,000,000 times more energy, kilogram per kilogram, when you go to fission. You get about 10 million times more energy when you go to fusion, and you get about 1,000,000,000 times more energy compared to chemical, almost 10 billion times when you go from chemical to antimatter. And earlier I showed you the rocket equation. Each of those different ways of liberating energy from matter gives you more specific impulse, and that's a number that you can plug into the rocket equation, and you can bring down, make it easier, essentially, to accelerate to appreciable fractions of the speed of light. And I'm having some trouble with this again, so I don't know if Andy, if you can go forward one slide, please. Okay, there we go. So what about the near term? So fusion starships are one possibility. So over here on the right is the Daedalus, which is arguably one of the most detailed Starship design studies that has ever been conducted. So actually, Icarus Interstellar was born out of what came after, essentially, Daedalus. So we came up with the idea of doing Project Icarus in 2009, but Project Daedalus was conducted in the 1970s by the British Interplanetary Society. It was a 5-year volunteer project. It worked on fusion pulse propulsion. Essentially you had these were big fuel tanks, and deuterium helium-3 pellets would be injected into a reaction chamber, and they would be ignited by relativistic electron beams. And deuterium helium-3 was used because of all the fusion processes. It gives off the largest fraction of charged particles. And those charged particles have kinetic energy, which can be channeled axially rearward from the spacecraft by this large magnetic nozzle. And the calculations, they had a target of Barnard's star, which at the time they believed harbored a planetary system. and the estimated top speed was 12% the speed of light, and so it would reach a nearby star system on timescales of a human lifetime. It's obviously vast, especially when you compare it to the Saturn rocket, but I mean, we've created structures that big before. It's no bigger than, for example, a Nimitz-class aircraft carrier. So what about the deep future? I'm really interested in the relationship between theoretical physics and technology. And so you've got this jump from the creation or the codification of the theory to the actual creation of technology. So, you know, it was the 1880s, roughly, when Maxwell came up with his equations of electromagnetics. And we're still over a century later utilizing those, you know, those ideas. They're critical, they're essential for cell phones, television, radio, radar, and all the modern, you know, wonders of technology we have today. Similarly, quantum mechanics envisioned in the 1920s by the German physicists, Schrödinger, Heisenberg, Planck, Born, Jordan Pascal. That was all a prerequisite to the creation of solid-state physics, which led to the birth of integrated circuits, computer technology. So, you know, the theoretical physics is the crucial foundation without which none of modern civilization, as we see it today, would exist. Similarly, with thermodynamics, the equations of thermodynamics, they are a prerequisite to the creation of things like jet engines and cars. And so what about the future? So what technology will human beings of the future be using from the theoretical physics of today? So this was the theoretical physics of the past. What about grand unified theories, dark energy, string theory, loop quantum gravity, extra dimensions? What weird and wonderful technology of the future in centuries to come may use this physics as its foundation? So, you know, recall that in 1897, it was J.J. Thomson that discovered or experimentally verified the electron. I think it's, you know, really interesting to just think that this is the era that created the theoretical physics that led to the nuclear rocket. I mean, this is Victorian England, where they were riding around on penny farthings. And I think in the future, you know, the era that discovered Higgs boson, dark matter, string theory, you know, the modern era will look equally quaint. So I'm going to move into warp drives and FTL now. So my work, I was definitely inspired by the work of Alcubierre. I just finished a 3-semester course on quantum field theory and started exploring some ideas. And inspired by a Kip Thorne-Yurtsever paper that came out talking about wormholes, I asked myself the question, what constraints do the laws of physics place on the abilities of an arbitrarily advanced civilization? So, you know, this is really not thinking about financial, sociological, engineering. It's really just looking at how physics constrains us. And so, before we can talk about, before I introduce the idea and the calculations, I want to discuss some of the fundamental ingredients, the recipe, if you like. And so, the first piece of the recipe, as touched on in the previous lecture, is that space-time itself is not limited by the speed of light. Objects moving through space are restricted to sublight velocities, but space-time itself is not. Another concept I want to talk about is that the universe is currently expanding, and now we know at an accelerated rate due to the existence of a ubiquitous exotic energy field that we've given the rather interesting and enigmatic name of dark energy. That extra dimensions may play a role in grand unified theories of physics. The question of something called modular stability, which was the focus of my PhD dissertation, which examines what holds an extra dimension compact, and something called the Casimir effect as well. So all these ingredients I'm going to talk about in a little bit more detail. So in the 1920s, Edwin Hubble discovered that the universe was expanding. So when he looked out and looked at the galaxies, he noticed a redshift, a shift in the spectrum. And analogous to how when we hear an ambulance coming towards us, and the pitch seems high, and then when it goes away from us, the pitch goes low, we have something analogous happening with light waves, that they are shifted towards the red. And you know, it's very interesting that wherever he looked, all the galaxies appeared to be receding away from us. And so, you know, this cry back almost to the geocentric model of the universe, that, you know, somehow Earth has some special place in the universe. But that's not the case. One way to visualize what's going on is simply the fact that it's the universe that's expanding. And so if you imagine the universe being on the surface of a sphere, this is a model, and you can imagine each of these little dots representing a galaxy, and you imagine that sphere like a balloon blowing up. From the point of view of each of these points, or each of these galaxies, it looks like all the other galaxies are rushing away from you. So there is no special point in the universe. Each point is special. From each perspective, it looks like everything is moving away from you. And so, in the 90s, we discovered, Miguel put up a chart earlier that showed the accelerated expansion of the galaxies receding from us. And so now we believe that rate of expansion is increasing. And could we ever harness that in any way technologically? So now moving on to the concepts, I brushed on the idea of extra dimensions. So extra dimensions have been creeping into physics for almost a century. So back in the time, around about the 1920s, they knew of two fundamental forces in the universe, so gravity and electromagnetics. We now know that there are two more, the weak and strong nuclear force. But people ask the very logical question, why two forces? Why not 7? Why not 12? Why not 50? More intuitively, why not one? Why not one superforce from which everything else is a manifestation, a low-energy manifestation of that superforce? And so Theodore Kaluza attempted to unify gravity and electromagnetics, and he added an extra dimension to the space-time metric of Einstein's equation. So instead of working with a 4x4 space-time metric, he added a 5x5. And he put electromagnetic vector fields and a scalar field in the extra fifth dimension. And after solving Einstein's equations, by varying the Einstein-Hilbert action, he was able to duplicate both general relativity and Maxwell's equations. So I'm going to say that again. By the addition of one additional spatial dimension to Einstein's equations, he was able, essentially, to unify the theory of electromagnetics and gravity. And then that brings about the rather obvious question of where is this fifth dimension? It's all very well to talk about it mathematically, but we don't see it. And so Klein, in 1926, came up with the idea of the Klein mechanism, where he suggested that the fifth dimension is compactified to a circle of extremely small radius. So the way to think about that is to imagine a one-dimensional line like a piece of string or something, and when you're looking at it from a distance, it initially appears to be one-dimensional. But as you zoom in with a big enough magnifying glass or microscope, you see that ostensibly one-dimensional line actually has a structure, an internal toroidal structure. And so this was the Klein mechanism. And so this was sort of how we reconciled the introduction of a fifth dimension. But there were criticisms of Kaluza-Klein theory in that it synthesized but didn't extend Einstein's theory. So there were no new predictions. I mean, general relativity had new predictions come from it. One example being the precession of the perihelion of Mercury. There are a number of other predictions from Einstein's general relativity. There was no new predictions. It simply synthesized the two theories. And then obviously there was no evidence for a fifth dimension. So here's the crux, that an extra dimension was required for the first, or one of the earliest, unification theories, grand unified theories. And extra dimensions have been cropping up ever since. So M theory right now is the most popular quantum theory of gravity that aims to unify all the four forces of nature under one a mathematical and physical framework. The ADD model is another popular model, or it was certainly popular when I was at graduate school. And something that Miguel touched upon earlier was the weakness of gravity. So gravity is about 10 raised to the 37th power times weaker than the next weakest force. And this is known as the hierarchy problem. And in the ADD model, we exist on a 3 spatial and 1 temporal dimensional brane, we call it BRANE. And the standard model particles and fields that we see are confined to the 3+1 brane, but that there is an extra, compact extra dimension of which gravity can propagate. And so you can imagine if this one force, gravity, has not only our standard 3 spatial dimensions, but also an extra dimension to propagate through, that is one reason for why it dilutes, why gravity is potentially weaker. So extra dimensions have been cropping up in physics for almost a century now, usually in the context of grand unification theories. So I'm going to talk about the Casimir effect now. So again, something that was touched on in an earlier lecture, in a previous lecture, is the idea of negative energy. So classically, the notion of the vacuum is that it's a region of space that's empty, that's devoid of matter. But we know from quantum field theory that that's not true. That space itself is this sea of virtual particles that come into and out of existence for very, very short periods of time. And these virtual particles, I mean, they become real for a very, very short periods of time. And so the vacuum is essentially this sea of not only particles, but fields. So protons, quarks, electrons, electromagnetic energy, they all come into and out of existence, and they comprise the quantum vacuum. And the dominant component of the vacuum is the electromagnetic vacuum. So when you see calculations on the Casimir effect, they will predominantly be talking about the electromagnetic Casimir effect, because that's the dominant contribution to the vacuum energy. So we know that from quantum field theory that every point in space is what we call a quantum harmonic oscillator, and specific oscillation modes represent the particles and fields that we see about us today. And we know from the uncertainty principle that no field oscillator can be strictly at rest. There's this vacuum wiggle, if you like, this zero-point energy, this vacuum energy. And the vacuum, there's an infinite array of freedom for what frequency the electromagnetic fluctuations can oscillate. So you can have these very, very long vacuum fluctuations, these very, very long waves. You can have very, very, very short waves. You have essentially an infinite degree of freedom in the wavelength or the frequency of the vacuum. So in 1948, the Dutch physicist Hendrik Casimir, working at the Philips laboratories in the Netherlands, came up with a stunning prediction. He said if you put two parallel conducting plates in a vacuum, the imposition of the boundary conditions on the vacuum would do something very interesting. On the exterior region of the plate, you have this infinite freedom on the frequency of the vacuum fluctuations. However, on the interior region, due to destructive interference, you can only have standing waves. So standing waves are like a half a loop, and then a full loop, and then 1, 2, 3. So you can only have, you've probably all seen standing waves from physics experiments, but you have essentially a restriction on the fields that can exist on the interior portion of the plates. And what this creates is essentially a pressure asymmetry in the vacuum that causes the plates to be pushed together. And this, to me, is absolutely remarkable. The fact that, this is a purely quantum phenomenon that is exhibiting itself macroscopically. So it's not it's not a force of attraction that is directly due to gravity, the real electromagnetic force, or either the nuclear forces. This is a force of attraction between two plates that's purely quantum. It's the most salient manifestation of the reality of the quantum vacuum. So this was predicted in 1948. It's been mathematically predicted. So you can plot this force of attraction as a function of the shape of the plates. You don't have to have square plates. It's been done for lots of different geometries. And it's been experimentally verified as well in the lab many, many times. Last time I looked, the most recent experimental verification was by Stephen Lamoureux of the University of Washington, who verified the Casimir effect to within 1%. So he looked at the mathematical prediction, and he verified it, and his results were within 1%. So this Casimir effect is real. It's not a theory, it's real. And we believe that the plate, here's the important part, the energy between the plates is less than the quote-unquote normal vacuum. And so this is what we call negative energy. So we were talking about negative energy earlier. We do know how to create negative energy. It's on the interior region of Casimir plates. So how do we calculate the energy between those two plates? Because what I said earlier is we're summing over an infinite number of degrees of freedom. And what we can take advantage of is something called the Riemann zeta function. So the vacuum expectation value, that's essentially the energy density of the vacuum, is given by summing over all the modes of the vacuum between 1 and infinity, and each of those ends corresponds to a different oscillation mode. And we know from relativistic quantum mechanics that E equals C multiplied by momentum, and we know P equals Planck's constant multiplied by the wave number, and so we have E equals h bar c k. We set h bar and c equal to 1, and we can put them back in at the end. And we know from the boundary conditions that the plates generate that sine kl equals sine n pi, and so this k is equal to n pi over L. And so you put that into this equation, and you have the energy between the plates, you take the pi and the 2L out, and you have the sum from n equals 1 to infinity of n. So you don't have to have a PhD in mathematics to know that the sum of the natural numbers from 1 to infinity is infinity. That is telling you to do 1, add 2, add 3, add 4, all the way up until infinity. However, this is actually, you can relate this to the Riemann zeta function. So this is a known function derived in mathematics from something called analytic continuation. And the Riemann zeta function is literally this. It says zeta of s is equal to the sum from n equals 1 to infinity of 1 over n to the s. And in this case, if s equals minus 1, then that takes the n onto the numerator and becomes essentially this. So the energy between the plates is given quite simply by pi over 2L times zeta of minus 1. And zeta of minus 1 is a function that it's a number. It's just a number that you can look up in a mathematical table, like Shams, for example. Zeta of minus 1 has a value of negative 1/12. And so the sum of the natural numbers to infinity is actually, according to the Riemann zeta function, negative 12. And what you're actually doing is you're extracting two infinities from one another to come up with a finite result. It's called dimensional regularization. And it's actually, just in these 4 steps, I showed you how to essentially extract infinities from an infinite result. So this Riemann zeta function is an incredibly powerful mathematical tool. And so you get that the energy between the plates for what we call a massless scalar field is negative pi over 24L. And you can take the derivative of that, the negative of the derivative, to get the force. That's a definition of force, essentially, to get this pi over 24L squared. So that gives you the force of attraction between the two Casimir plates. So, how does this all fit into warp drive? Where am I going with this? Well, what we can do now is what I want to do, or what I did for my dissertation, is, okay, so I'm going to explain the concept here to you. So if you imagine, so we've got normal space, it's 3-dimensional space, and then you've got the extra dimension. That extra dimension, mathematically, is isomorphic to the two parallel plates. So that 0 and that location, 2 pi, after one complete revolution, is exactly the same as putting a plate here, going around once, and putting a plate at that same starting point. It's mathematically isomorphic. It's the same thing. So just by having these boundary conditions of this periodic extra dimension, that's exactly the same as having 2 parallel plates. So that's the key kind of thinking here. So in the extra dimension, you have a Casimir effect that's mathematically the same as, isomorphic, as having 2 parallel plates. And as you bring those plates together, you increase the vacuum energy density. And that's isomorphic to shrinking the extra dimension. So the smaller the extra dimension is, the bigger the vacuum energy. Now, earlier I said for the calculations, the dominant contribution is the electromagnetic contribution. What I did for my PhD dissertation was look at the contribution from all standard model fields and particles. So this is the Casimir energy contribution in the extra dimension due to all the standard model particles and fields. And so that was sort of the crux of the calculation. And so we can do this for what we call an M4 cross T1 manifold. So M4 corresponds to Minkowski space. That's normal flat space that we see. This T1 stands for a toroidal. That's a circular extra dimension. And as previously, the energy is related to the wave number, so that's for the continuous part of the energy calculations. But then you have this compactification as well. So essentially, so this is the contribution from the extra dimension. So these are the 3 spatial dimensions. Here's the contribution from the compact extra dimension. And to calculate the Casimir energy density, we have to do an infinite integral plus an infinite sum to capture the contributions from the Casimir energy in both the Minkowski space and the toroidal compactified extra dimension. And there's about 20 or 30 lines of calculations to get from here to here. So I utilize something called the gamma function and the zeta function to regularize the integrals and the summations. And I uploaded a paper to the archive called the Zeta Function Approach for Casimir Energy Calculations in Higher Dimensions. So that's the archive address. So if anyone's interested in seeing the explicit calculation of how we get to this result, you can go to this paper. But essentially, the Casimir energy in the extra dimension is directly proportional to the size of the extra dimension raised to the 4th power. So it's strongly related to the size of the extra dimension. It's strongly coupled, we say, to the size of the extra dimension. And everything else in this, I mean, it's important, but they're just constants. They're just numbers. These are just numbers. This is just a number. And what's the important point here is this 1 over r to the 4th relationship. And then we can do that so earlier we did it for a massless scalar field. So a scalar field is the most elementary object in quantum field theory. Typically, physicists will look at the physics of a scalar field and build up from that to vector fields to build up a full picture of the physical model. But we start with scalar fields, and we started with a massless, and now we're going to go to a massive scalar field. So similarly, we can calculate the Casimir energy due to the continuous modes of the vacuum, the compactified modes in the extra dimension, and then the mass contribution. And so, similarly to before, we use some interesting mathematical machinery, including something called a modified Bessel function of the 2nd kind, and we come up with this Casimir energy density due to a massive scalar field in this space-time manifold. And the Casimir energy density is coupled to the mass of the particle, raised to the 5 over 2, the radius of the extra dimension, raised to the 5 over 2, and then this modified Bessel function. So just like sine is a function, just like cosine is a function, well, this k is a function. It has a specific shape that you can use your favorite mathematical tool to plot. So using knowledge, why am I doing this? So using knowledge of supersymmetry multiplets, you can actually, once you've got those previous calculations that I showed you, you can actually come up with relationships to get the Casimir energy contribution from all standard model particles and fields. So these are all the fields and particles that we know in nature, including the Higgs field. So why do we do that? Well, what we're going to do next is look at the contributions in the 5th dimension from all the standard model particles and fields and see what kind of an energy profile that gives us. So if we look at this plot here, on the y-axis, we have the energy contribution, and on the x-axis, we have the size of the extra dimension, which we don't know. But using those functions that we showed previously, we can plot out the Casimir energy for a range of different radii by adding up the contributions from all of the different particles and fields in the standard model. And I was looking for what we call a stable minimum. So a stable minimum is a place that the extra dimension likes to sit at, because what's natural is for a dimension to either want to contract or expand. So our macroscopic spatial dimensions we know are inflating. We know that space-time is expanding. It's actually natural for a dimension to want to either contract or expand. And so what I was looking for was what we call a stable minimum. That's a point, a specific radius of the extra dimension that there's what we call a stable minimum. So you can imagine a ball rolling down a hill, and it likes to sit at that stable minimum point. I wasn't able to find a stable minimum just with the standard model fields, but with the injection of one exotic massive fermionic field. Again, that had motivations from a paper I read by a famous particle physicist called Mohapatra, who postulated the existence of something called a bulk sterile neutrino. And so the addition of one additional exotic field, we summed the contributions, and I was able to find a stable minimum of the extra dimension. And what was actually, so what's interesting about this? There's two things. One, in this model, this mechanism can be responsible for stabilizing the compact extra dimension. And two, that this sits at a non-zero energy. And so this begs the question, could this be the cosmological constant? Could Casimir energy in the extra dimension be the source of this energy that is causing the inflation of space-time? Okay? So that's kind of the crux there. And if it is, if there is this relationship between the size of the extra dimension and the cosmological constant, then could that be technologically manipulated in some way? Could that be one solution to FTL propulsion? So what's the story so far? So the Casimir effect, or the Casimir energy, can be identified as the source of the cosmological constant and is related to the size of the extra dimension. So that's the crux that I want you to take away from this. That the cosmological constant, which generates the expansion of space, is related to the extra dimensional radius. And so, so how can we relate this to exotic or novel propulsion? Well, the idea is quite simply, so here's the idea, that in the region of a spacecraft, the fifth dimension, you don't have any modification of it, but at the front of a craft, using some technological mechanism, this little black box, you shrink the size of the extra dimension, and at the rear of the craft, you expand the extra dimension. And then the idea was that this would be isomorphic to the Alcubierre metric, where you have this asymmetric mutual contraction and expansion of space-time at the front and the rear of the spacecraft. And so in effect, you're bringing the object closer to you and you're getting further away, not by traveling through space, but by manipulating space itself, by performing this asymmetric contraction and expansion. Essentially, you're traveling without moving. And so what I want to do now is do some calculations that show, all right, if we wanted to use this model to accelerate or to go at the speed of light, how much would we need to modify the size of the extra dimension by, and what energy conditions, what would the energy requirements be? So we saw earlier that for the massless scalar field, the vacuum energy, which we identified as the source of the cosmological constant, which is proportional to 1 over the radius of the extra dimension to the 4th power. And we also know from the Friedmann equation that Hubble's constant is proportional to the cosmological constant. And Hubble's constant codifies the rate of expansion of space per unit distance of space. So we know that Hubble's constant has a value of 70 kilometers per second per megaparsec. Now, what I did at graduate school, and this just made Hubble's constant all the more illuminating, was turn that into SI units. So I turned that into meters per second per meter. And so Hubble's constant is actually 2.17 times 10 to the minus 18 meters per second per meter. What that means is if you had 1 meter of empty space and you waited 2 billion years, that 1 meter of space would then become 2 meters of space. So I thought that was illuminating to do that. But we don't want to wait 2 billion years. We want to do that. What we want to do is have space not expand at that rate, but expand at the speed of light, which we know is 3 times 10 to the 8 meters per second. So this simple ratio here tells me by what factor I need to amplify the value of Hubble's constant to have light speed expansion. So rounding up speed of light, just say we're doing back of the envelope calculation here. So rounding up speed of light at about 10 to the 8. We know that Hubble's constant is about 10 to the minus 18. So back of the envelope calculation, we need to amplify Hubble's constant by a factor of 10 to the power of 26, so that a region of space is expanding not at 1 meter after 2 billion seconds, but at the speed of light, essentially. And again, similarly, because we know this relationship, we can say by what factor we need to increase or change or adjust the radius of the extra dimension. And so it's a factor of 10 trillion, essentially. So if, again, by some little black box mechanism, we can modify or interact with or adjust the size of the extra dimension by a factor of 10 trillion, then under these calculations, it will have the characteristics of an FTL spacetime. And then how much energy would we need? How much energy would we need to do that? Well, this is the accepted value of the cosmological constant, 10 to the minus 47 GeV raised to the 4th power. Again, I think it's instructive to just convert that into SI units. That, to me at least, is a more meaningful number than that. And so cosmological constant is 1/10 billionth of a joule per cubic meter. And again, we know from that previous slide that Hubble's constant is proportional to the square root of the cosmological constant. And we saw earlier that we needed to increase Hubble's constant by a factor of 10 to the 26. And so because of this square root relationship, we need to increase the cosmological constant by a factor of 10 to the 52. And so if we increase this number by 10 to the 52, for a light speed expansion, for a speed of light expansion, you'd need a cosmological constant to be 10 to the 42 joules per cubic meter. And then this is a very, again, back of the envelope calculation. Let's say that this space-time expansion needs to encapsulate a spacecraft on the order of 10 by 10 by 10 meters. So 1,000 cubic meters. We just multiply this number by 1,000 cubic meters and we get 10 to the 45 joules. This could be modified. We don't really know how thick a warp shell needs to be. I mean, in principle, it might just be Planck length. You don't know. So this is definitely an upper limit calculation. But if you've seen the, it talked about that warp drive speed of light would require the mass energy of Jupiter. That's directly from this calculation that came from my paper. And so in the early calculations that were done on the Alcubierre drive, we saw that you'd require more mass energy than was available in the known universe for light speed expansion. And then this brought that calculation down to about the mass energy of Jupiter. So we need to create an anti-Jupiter, annihilate it, and we'll get to Alpha Centauri in just a few years. There's a number of leaps of faith here. I'll be the first to admit this. This isn't the solution to warp drive. This isn't going to lead to a working warp drive. This is something I came up with. It made up a chapter of my PhD dissertation. You heard Miguel speak earlier. He was working, I believe, as a postdoc when he came up with his idea as well. And we're not funded. We're not even encouraged really to look at this. I was very grateful that I had an understanding PhD supervisor who didn't mind me actually trying to publish a paper on warp drives. He was supportive, but that's typically not going to be supported in universities. And I think you need more of that. I think we need more of that. I think we need 10 graduate students or postdocs or professors or 100 or 1,000 or more, all looking at this problem from different angles to try and make breakthroughs and come up with shifts in paradigm that may one day allow us to reach the stars. So obviously some of the questions here are higher dimensions real? Is the cosmological constant high dimensional Casimir energy? Could they even be manipulated? I mean, that's one of the key questions. And could we generate a sufficient amount of energy? All of this is backed up by mathematics. So there are calculations that are in peer-reviewed journals, Journal of the British Interplanetary Society, Journal of Geometry and Physics, JBIS again, Modern Physics Letters A. And I also wrote a popular science version that you can see here that talks more about the concepts and the ideas. But like I said, my dream is that one day we could, people aren't encouraged to look at this. The theoretical physics community isn't encouraged to look at this. But my dream is that one day we can galvanize the theoretical physics and the particle physics community together to look at these problems and perhaps turn interstellar flight from imagination into reality. Thank you so much, everyone. Mr. Zoltan. Yeah, that was a good question. So all of the different particles and fields came up with different contributions, some of them negative, some of them positive. And without the introduction of the exotic field, there was just a graph that looked like this. It wouldn't have led to a stable minimum. But with the injection of that one additional field, we created a stable minimum of the potential.
How did you discover that?
Gosh, that was a few years ago. That's a good question. I was playing around in Mathematica. I'd summed all the contributions from all the standard model fields. It wasn't working in a way that I'd hoped to see, and so I started experimenting with different fields. But yeah, good question. Thank you. Yes.
The speed of warp. You calculated the energy requirements, and I just wanted to ask something about what is the real version of warp 1 to warp 9, and what energy requirements would they have?
That's a really good question. Okay, so I'm going to go slight tangential. I don't have, so warp 1, I think, I used to have the Star Trek technical manual when I was a kid, when I was about 15 years old. And the gentleman earlier asked about dilithium crystals, and I wanted to correct him and say that dilithium crystals are actually porous to antimatter, and that's why dilithium crystals were used, because they could direct the flow of antimatter. They weren't actually responsible for the warp drive. So I think I memorized when I was about 15 years old the different warp factors. I think warp 2 was 10 times the speed of light, all the way up to warp 9, which was 1,516 times the speed of light. I haven't done those calculations. I didn't even think of that. I should do. But what I did do, which I think is quite interesting, is say, okay, so earlier I showed that you shrink the extra dimension by a factor of 1,000 billion. What would be the maximum you could ever shrink an extra dimension to? Well, I said, okay, well, the maximum you could shrink it to would, let's say, be the Planck length. So I did an energy a top speed calculation based on shrinking the extra dimension to the Planck length, and came up with a top speed that the highest speed you could ever reach with a warp drive as being 10 to the 42 times the speed of light, which would be crossing the known universe in a fraction of a second. But it would take something like 10 to the 90 joules of energy, something crazy. Any other questions before we move on to Tiffany? Yes?
What about if you increase the number of the smaller dimensions, for example, compared to M theory?
I think that's an absolutely fantastic question. So all these calculations, this was all based on the most basic model, three spatial dimension, x, y, z, one temporal, and one toroidal extra dimension. Of course, actually in my PhD dissertation, I do the energy calculations for a donut, a T2, a torus, a T2 torus, a donut essentially. And then, of course, the full string theory is built in a Calabi-Yau manifold, which is an incredibly complex and sophisticated high-dimensional mathematical object that's necessary for string theory to work. And I think that would be an absolutely fascinating way to continue this line of research. You know, we did the calculations for the simplest high-dimensional space-time geometry, and of course you could start extending this idea to more complex geometries. I think that's a good question. I'd love to do that one day. Damien. That's a good question. That's a really good question. So like I said, it was from a paper by Mohapatra, which proposed the existence of a bulk sterile neutrino. I'd have to go back and reread. And it's been a few years since I've looked at this, so I don't know the answer directly. But I'm sure we could ask Mr. Google, and he'd tell us quite quickly. All right, thanks a lot, everyone. Appreciate it.